Vicinaqua stands for Integrated Aquaculture based on Sustainable Water Recirculation System for the Victoria Lake Basin. So this I already said. I'll do the introduction and then Julian will talk about the technologies. It's a program funded by Horizon 2020. It's a 3-year program that started in 2016 and ends in May 2019. We have one pilot location where we will set up the whole project, which is in Kenya, around, close to the lake, in a place called Kisumu. And we're working with 10 other partners on this project. We have African partners and we have European partners. And they work on different aspects of the program. Lake Victoria is the second largest freshwater lake in the world, and it's very important for the region. So you have 3 countries bordering the lake: Uganda, Kenya, and Tanzania. And we have partners from all those countries in the project. The idea of the project came because there are some problems at the lake. The population is growing fast. The people are poor. There's a poor sanitation. There's more and more fish processing industry, and all the water of the sewage of these industries ends up in the lake, which results in over-fertilization. And you can see the picture there in the corner. So a lot of places in the lake are covered by these water hyacinth outbreaks. When we visited there, we couldn't see the water. It was just flooded by this water hyacinth. Then they overfish the lake as well, and there's a lack of awareness among the people who live around the lake. So the aim of the project is to develop a multi-purpose self-cleaning filtration system that sanitizes the wastewater systems of the municipal water and the fish processing water, and reuse this water in a RAS system. And then the whole system is supplied by renewable energy. We have PV, we have biogas, and thermo generator as well. Then there are some other activities: awareness raising, capacity building, and knowledge transfer among the stakeholders in Africa. So our role in this project is to, we lead one work package, which is basically setting up this pilot, so constructing, designing, constructing, both, and then mainly the RAS system and all the other aquaculture activities that are in this project as well. The main objectives of the project, the green ones are the ones that AquaBioTech is responsible for. But the objectives are, so we're making a water treatment system using self-cleaning membranes. So these membranes are also developed in the project by one partner. And then the next step is to set up a membrane bioreactor in which they will test these membranes that were developed in the project. So the idea is that clean water comes out, which we will reuse for a hatchery, powered by what I already said, by renewable energy, which another partner takes care of. All these processes are monitored with an online monitoring system. Then when the pilot is built, we will do trials with different membranes, with commercially available membranes and the developed membranes in the project. And we will also test the hatchery, obviously. Then the African partners are mainly responsible for impact assessment, socio-economic studies, things like that, awareness raising, capacity building, and knowledge transfer. And the last objective is to foster gender equality. This is a big EU, I think they put it in every project. This is the concept of the project. So you start with wastewater, domestic wastewater, and fish processing wastewater, which goes through the Mbr. The green one in the middle, the self-cleaning particle filter, is taken out of the project because it was too high cost. It's not applicable to Africa at all, and it was not needed. The water was clean enough, so we didn't need this filter. So it directly goes into the membrane bioreactor, And then the water that's cleaned is going to the RAS system and as well as agriculture.
If it's domestic waste, how can it be clean enough?
No, it will be cleaned, but it doesn't need this filter first. The Mbr will clean the water. That's the treatment system. Okay. Yeah, and then so it's powered by the PV and the biogas, and it's monitored. Yeah. I have some flyers here with this picture as well. If you're interested, you can take one later. All EU projects, they are based on collaborative, so setting up a collaborative framework to enhance the local capacities. We created a stakeholder score group with African partners and European partners. We'll do training sessions. So for example, me and Julian will travel to Tanzania next month to do a training on aquaculture. There's a student exchange program that brings African students to all the European partners that are universities, the research partners. We have a knowledge platform which is not uploaded yet, that's why it's a bit grayish. It will be on the website, and we have study visits. So this will all be in Africa, where the African partners and the stakeholders, they will visit, they will arrange visits that are related to biogas plants, aquaculture, and these kind of things. It's a 3-year project. I already told you we are now halfway. The idea is that in December we will start building the pilot, and in next May or June we will start the trials. The impacts we're trying to address is to improve the sanitation in the area. And the idea is that the project will be scaled up later in the other countries as well, so that they adopt the technologies that we develop in this project. Fresh water availability, avoiding more fertilizers into the lake, antibiotics. So by reusing the treated water from the waste. Use of renewable energy to have a low impact, low CO2 footprint of the project. Life cycle analysis, environmental impact assessments to make sure that we follow all the environmental regulations in the country. The extraction and use of natural byproduct, so we will reuse the nutrients as fertilizers in agriculture. We're also planning to set up a small hydroponics in the system if we have enough budget for it. So hopefully we can also use it there. Otherwise we will only use it in soil agriculture. And we also want to promote aquaculture, obviously, in the region by the hatchery. So there is already a lot of pond aquaculture, but they have a lack of fingerlings. That's why we chose to set up a hatchery.
Each country is going to have its own pilot?
No, for the project we have only one pilot, but there's partners from the other countries as well, so that will be the follow-up, basically. So we will, within the project we will design an upscaled system, because this is just a pilot, but we will already make the design of an upscaled system, so these countries can adopt this as well. And then the more social activities will also have an impact. We will try to raise awareness among the community around the lake to ensure environmental protection, food security. The main focus of the project is sanitation and water supply. There's economic benefits for the people in the long term and job creation, and they would like to encourage women to be more involved in the aquaculture sector. And this is the initial design of the pilot. So on the left side you have the hatchery. It will be a small, really small tilapia hatchery. So you have the broodstock tanks in the bottom. You have egg incubators, larval rearing tanks, and the nursery. We will make them around 1 to 2 grams. but Julian will tell you a bit more about that. And then you have the space for the Mbr, the biogas digesters, and the agricultural field on the top right. And these are some hydroponic area. Hopefully we can make it. It's supposed to look like that, except the background. And then I'll give the word to Julian. He traveled to Kenya a couple of weeks ago for the site selection. So they selected a site where we are going to build this.
The aim of the project is to show that we can use wastewater for aquaculture and agricultural purposes. So there's a big focus on water reuse. Another big part of it is to make the technology appropriate for the setting. So it's useless having something which is installed and doesn't run for the long term. So a big challenge of all of this that we'll be speaking about is making membranes. Often you don't think of membranes as something suitable for this context, something suitable for the setting. The site is a wastewater treatment plant, which is the largest wastewater treatment plant in the area. It's a passive system, so it's wetlands. It's a number, not wetlands, it's a number of ponds and then a wetland at the end. So water comes in basically you have just an intake, so a constructed area for the intake, and all you have is a mechanical screen like you have at any wastewater treatment facility, a coarse screen, and after that it's by gravity. So at the top you have an anaerobic pond, and then what they call the facultative pond, the larger one, and 2 maturation ponds. In the last 2 ponds, at the moment they grow fish, and the people from the surrounding areas try to catch these fish, but they're trying to. It's a problem is people stealing fish from this wastewater treatment plant. So these are some pictures. This is the anaerobic pond, the first pond. Okay, the intake is somewhere here. And our site is going to be where those people are standing, so just next to the facility. There are 4 main parts to it. There's the membrane bioreactor, which is the wastewater treatment plant, essentially, which I thought I'll spend most time explaining, because I thought this could be something which could be of interest here. So my main focus in this presentation is the Mbr. I'll explain the other parts too. Membrane bioreactors are upcoming, now commercially available and very, very popular wastewater treatment technology, which is it's mainstream. So it's not something. It's something which is very common, particularly for reuse applications. So economically. In municipal settings and industrial settings, you install a membrane system, a membrane bioreactor, when you want effluent of a certain quality. Obviously, an Mbr basically combines 2 wastewater treatment processes. So you have the activated sludge process in a typical wastewater treatment plant. I'm sure you've been. I don't know if you've been. You have activated sludge process and then large settling tanks, where you basically separate the biomass from the water. In this case, in a membrane bioreactor, you are combining the membrane process in the activated sludge tank. So you're separating the water and the sludge using a physical process. The advantages of a membrane bioreactor are obviously the high quality of the effluent, because you have a physical process. We'll speak a bit about this later. But also the ability to decouple the SRT, the sludge retention time, and the hydraulic retention time. So you can increase the biomass in the sludge tank. So typically you're operating at 6, 7, 8, 9, 10 to 12 grams per liter. And this has its advantages as regards the degradation of certain organic compounds, which shorter sludge retention time could be harder. So you have this high MLSS, and you have this clean water, a good quality at the end. Often, one advantage which is mentioned is the fact that you have a much smaller footprint, because sedimentation tanks usually take up quite a big space. As regards Mbr configurations, there are typically three configurations. You have a side stream configuration, which was the first ones which we started up. So often this is done for a retrofit. So you have a typical activated sludge tank, you pump water from there, pressurize it, and have pressure vessels where we speak about cross-flow filtration. So the water, I'll speak about it in the next one. I'll speak about it in the next slide. And then the other two options are either putting the membrane inside the activated sludge tank. Okay, so the first one is external, the second one is submerged, and the third option is submerged but in a separate tank. So you have membranes in a separate tank. So these are, I wanted to try to give the these are the main commercial technologies are the following. So tubular, so these are the ones which are the external ones. You have pressurized vessels where the sludge is typically pumped in the center of the vessel, pumped inside the membrane, and it goes from inside out. Flat sheet membranes, now I'll speak a bit more about them in the next slides. Flat sheet membranes, where typically you have two membranes with a spacer in between, sealed on the outside and a pipe on the top, and you're creating, you have a negative pressure where you're sucking and letting the water pass through. And then also very popular are hollow fiber membranes, where you have strands of membranes, many strands grouped together, and again the water is going from inside the sludge into the center of the membrane. This is a representation of the external membrane. Okay, so this is what we call cross-flow filtration, as the same as reverse osmosis. So you have the feed is coming in here. Because it is under pressure, the water is passing through the pores, and the permeate is around. So the permeate is taken out of here, and you have a concentrate, which is normally returned back into the sludge tank. These are different configurations of often what we use often are ceramic membranes in these, or tubular membranes. Then I want to speak a bit about dead-end filtration. So for example, when we're speaking about these tubular membranes, we have, when the water is passing through the membrane, you obviously have a certain amount of clogging of the membrane. And we control this amount of clogging on the membrane by either backwashing, so in this case, pushing the water back from the permeate side back to the feed side, lifting this cake, or else having relaxation periods. So in the normal operation, you are passing water through, and then you stop this permeate cycle and just allow a relaxation cycle where the air which is traveling on the surface of the membrane scours the surface to control this caking effect. And this is a typical installation of a flat sheet. So basically you have a number of sheets, typically with a surface area of about 1 square meter, 1.2 square meters, lined up near each other, connected to a manifold. As differences between the two, between external and submerged, so this is an external membrane process and a submerged. So the membrane is physically within the biological reactor. The main, when you speak of membranes, people are always speaking about costs. As aeration costs, a big part of your cost is in the aeration. So this bubbling of air underneath the membranes, both for hollow fiber or for these flat sheet membranes, to control this membrane fouling. For cross-flow filtration, you do not have this aeration. But then you have the cost of pressurizing the water, of pumping. The flux in these pressurized membranes, again, is much higher than the submerged membranes. The cleaning frequency, obviously, is also higher in the pressurized. And as regards operational and investment costs, the operation, which is always a trade-off, as operational costs for the pressurized one is higher because you have this higher pressure. I wanted to just give an idea of a few terms which you probably know about, but when you're speaking about membranes, these terms are absolutely critical. The flux, which is the amount of water passing through a unit area, which is often expressed as LMH. So whenever you're reading something regarding fouling and membranes, the flux is something which you need to, is the first thing to look at. The transmembrane pressure, which is the pressure between the clean side and the dirty side. The permeability, which is basically the flux all over the TMP, because obviously as you're increasing the flux, your TMP is going to increase. So this is something. And the resistance of the membrane is often defined as the clean water flow plus this cake, this cake layer. And in membrane bioreactors, we often speak about this SAD, which is the amount of air you need to keep the membrane operational, either per unit area of membrane or per unit flow of permeate. In submerged membranes, the key is aerating it. So underneath you have a number of diffusers, coarse bubble diffusers. So you have bubbles flowing on the surface of the, it will be on continuously. The trick is optimizing it, is seeing how low you can go, how low you can go with regards to how little air can you pump over the surface of the membrane to keep your flux stable. So to clean, to avoid this caking layer, to avoid a certain layer building up. So basically, as the water passes, so if you have a membrane with water passing through the holes, obviously you're going to build up a certain layer. I have pictures, but you're going to build up a certain layer which is going to increase the resistance for the water to pass through. So for submerged membranes, without this action of bubbles over the surface of the membrane, you will clog really, really quickly. So in the hollow fiber ones, we do have backwashes. So often you'd operate for 8 or 9 minutes in permeate mode, in suction mode, and then 1 or 2 minutes pushing this permeate back through to lift this caking.
Don't use air.
There, you would still have air. So you'd do this discontinuously, but the air in a submerged membrane is a continuous process. As fouling, if you're speaking about any membrane process, whatever membrane process you speak about, fouling is the key question to always keep in mind, because it affects your design parameters, it affects how you operate. It's a big operational headache, so it's something you need to keep in mind. And when we speak about fouling, we're speaking about this loss of permeability over time. Okay, so ideally, the permeability remains constant over infinitely, but membranes don't work like that. So typically, we speak about 2 types of fouling of this. So I have fouling, which is a general cake on the surface of the membrane, and clogging, which is where you're blocking the pores. What I wanted to bring about here is that there are many factors which affect fouling. So a big part of it, for example, is the quality of your biomass. If you need to monitor your biomass continuously to control your fouling. So whether it's the size of flux, CPA, so your biomass is one thing you need to really take care of. The other part is the characteristics of your membrane, and then how you are operating it. So flux, TMP, so the design of the system. So basically what I wanted to bring about is that when you're operating a membrane system, all of these factors will come into play. And then I wanted just to give an idea of fouling in terms of, so you have different types of fouling. reversible and irreversible. The reversible thing is what you normally get in the short term. So in a normal cycle, if this is your permeating cycle, okay, and this is your 1 minute of relaxation or your 1 minute of backwash, okay, over time you can recover back to the average is back to where you started. So this is reversible fouling, and this is on each cycle you're going to get that. So it is fouling on a superficial fouling. The irreversible is something which over time you're going to see that the TMP, the average TMP of each cycle is increasing. For this to get back to the original average TMP, you have to use chemical cleanings. So you're seeing the change in pressure, so the change in this differential pressure over a cycle. So normally you'd say the TMP has increased over when I used to operate these facilities, would say like the last time we had this jump was in a period of time, so over a period of time. Obviously, you have a certain amount of membrane degradation. So chemical cleanings and these things affect the properties of the membrane, and ultimately the membrane has a certain lifetime. You normally plot, so on your monitoring system with a membrane system, you're always going to monitor your TMP. This is absolutely essential. And as you see it, you're always going to see these spikes. So in the normal operation, okay, you're going to have these spikes. This drop is either a backwash cycle or chemical cleaning in terms of flat sheet membranes, okay? So this is the reversible. Typically, in my experience, there are lots of different things, but what we would always use is first you clean it by hand with a very soft cloth, because the cake on it, or if you use a jet of water, you could damage the membrane. So we used to first clean it by hand, wash it, and then soak it first in sodium hypochlorite to remove the biological part. And then, if you have inorganic fouling on the membrane, you'd do an acid cleaning. So often it is a mix of the two. First, a manual cleaning. If you have hollow fiber membranes, again, you first remove the solids entrapped within the membranes with water and trying to be careful not to pull any. And then you put it into a tank and clean it. So you could also, if you have in hollow fiber systems, you could also do a chemically enhanced backwash. So in your backwash, you wouldn't want this to be done continuously, but you'd say, okay, once a week, I would put some hypochlorite, a little bit. You have to be careful how much you use because of the effect of the sludge, of it on the sludge. But sometimes you would do it. But I never, because it's a bit tricky. But over time, you have this TMP is continuously increasing. And basically, this determines how many membranes you would exchange per year. So a membrane has a lifetime, and you have to, in your OPEX costs, you need to account that a certain amount of these membranes have to be changed. I mean, I know systems have been operating for 6-7 years with the same membranes, changing very, very few, which they hit when they're cleaning. But this depends on how hard you press the membranes. If you work at high fluxes, you're not going to last for so long. It's always a balance between how much you spend initially and you buy loads of membranes, how much space you have. If you can afford to do that, so operate the membranes with a very, very low flux. But obviously, ultimately, it comes balance. It's an economic decision. Here, I wanted to give an idea of the time frame that we're speaking about. So the reversible is removed by either the backwash or the relaxation period with And this is something which is a per cycle. So every 10 minutes, you have this reversible fouling. This residual is something which you need these maintenance cleanings. Irreversible, again, is something which is, you would normally clean the system, you would design the system to clean it once every 6 months. We used to clean every 6 months, but it depends on. And recoverable is the lifetime of the membrane. This is the sludge I am speaking about. The interesting thing about like this picture, this is very typical of, I worked mostly with flat sheet, but this is very typical because you could see the path of the bubbles. Possibly in this system we had to open up the aeration a bit more to make sure that the bubbles are reaching the membrane more evenly. What I want to say is that membrane bioreactors are something which are becoming more and more common, particularly for the industrial sector. So industrial reuse is something which is, there's a big market for it. What I want to convey here is that if you see an application for it, there's so much knowledge from the wastewater industry that the prices of membranes, I don't know here, prices of membranes are dropping a lot. Like in RAS, I don't know if it's something which there have been some, I don't know if you spoke about it here, using membranes in RAS, no. It's something which people have tried, but economically is difficult, it's still difficult to justify. It's something which I wish to explore because but it's something difficult to justify. Again, I just wanted to show that the cost of an MBR, which when you speak to utilities, people typically think that an MBR is much more costly than a conventional activated sludge. But typically, it is relatively similar. As regards the OPEX, the operational costs, you have a big part of it, which is this aeration. The aeration is a big cost to keeping a membrane running. Physical and chemical cleanings, membrane replacements, these are things which are only in MBR. But then the aeration for the biomass you have even in conventional systems. This is showing the price over the years, how the membrane cost has decreased so much that it made a big difference in the price of membranes. Yeah. What I want to show here is that in your OPEX, a big part of your cost is aeration. You're speaking about 70% is just aeration. And cost of chemicals, people speak about cost of chemicals. In reality, it is labor rather than cost of chemicals. So here you could see as an MBR energy demand, the big part is process air for the blowers, for the biological part, and the membrane aeration blowers, which make up a large proportion. In wastewater, we speak a lot about kilowatt hours per cubic meter of water treated. This gives an idea. In reality, membrane systems are higher. So although that 0.48 is close to this 0.6 for a submerged MBR, in reality, the reality is that it's not on this side, it's more to the other side. So you're looking at more at a 0.9 to 1 kilowatts. Now, back to Vicinaqua. What we're trying to do in Vicinaqua is create an MBR, which is suitable for use there, suited for use in Kisumu. We spoke a lot about fouling. Our Italian partners in the Institute of Membrane Technology do a lot of work on membrane coatings. So basically, they are applying a surface on the membrane, on a commercial membrane, using this PBM technique. I don't know much about it because it's not my area, but if you are interested, I can direct you to my colleagues. But basically, they are creating certain properties, so of hydrophilicity and smoothness on the surface of the membrane to reduce the amount of attachment of this cake. And always the objective of this is to reduce the amount of air you're blowing. So the whole point of this part of the Vicinaqua project is to reduce the amount of air, the amount of energy we are consuming in blowing this air over the membrane. So that is one part of it. they're and they have got pretty good results, and are currently testing them on a small scale. So I don't know, 0.8 square meter membrane, so in the lab. Now in the pilot facility, they will have two systems, a conventional one and this modified membrane to compare. And then the other part, which is more ambitious than the first part, is that they are introducing compounds into this surface, which when activated by hydrogen peroxide or UV light, and I think here they're mentioning, or an electrical current, yes. So they're working, its releases, I'm not going to try and explain this because I can't. But by activating some certain compounds on the membrane surface, you release oxygen bubbles, which could lift this fouling layer. And now this seems like something which is quite detached from something which has to be built in Africa. But in reality, if we do manage to prove this, it will be basically, it will reduce the cost of operating the system. As regards the energy supply system, there are two parts to it. There's the biogas part and the photovoltaics part. The biogas part is mainly taken care of by the Kenyan partners at Jomo Kenyatta University, and the photovoltaic part is done by a German company called BPE. As regards biogas, the volumes of solids from the facility are small. So we have some solids, we'll be collecting solids from the RAS, collecting biomass from the MBR, but as regards how much we can take from this to power the facility, it's a very small percentage. To increase this, they're going to harvest and chop up and dry water hyacinth, which there is a lot of. So this should increase a bit of our biomass. There are a number of large storage tanks, which look like something like this, with sample points along the way. And they're going to use a petrol generator. There's a certain amount of cleaning involved, and the compressor, a tank and the compressor. And then to make it a bit more complicated, because in this project they want to complicate things, and they're also coupling what they call TEGs, Thermoelectric Generators. And this is something which in the past the cost of them was very high, and now the prices are dropping. So basically what a TEG does is, based on the Seebeck effect, uses temperature differences to create a current. So
the temperature differences from the biogas processing?
From the generator. So basically, in this case, for the biogas part, they are mounting them on the generator. So the generator is emitting a certain amount of heat, and they're trying to recover a certain amount of this heat from the heat generated by the generator, which is run on the biogas. But again, as part of the whole process, it is a small part, but they want to show that it could possibly be feasible. So here, they're looking at this to increase this power output, which in reality, to create a high power output, you need to have many of them. You need certain parameters. And then the second part is the Sogena system, which is a standard photovoltaic system coupled with this TEG system. So basically, if I understand it correctly, they're putting TEGs around the frame of the photovoltaic system and at the back. So you're from the ones on the around it, you are taking the direct radiation from the sun. On the back side, you are taking this temperature difference between the PV and the backside. And for this, they're also putting them inside the ponds to have a larger temperature difference. And I think, from what I saw, the biggest effect is actually in cooling the photovoltaics. So when you cool down the photovoltaics, the amount of energy you can recover increases. So I think from all of this, but you can read more, or if you're interested in this, I can direct you to our partners. The biggest advantage from this is actually the cooling of the photovoltaics. And then, as regards the RAS, we didn't include a lot in here, but we're designing so basically it's the capacity of 25,000 fingerlings at 1 to 2 grams, all male. The system is made up of three systems: broodstock and egg incubation, a larvae and a nursery. And the system is being designed in such a way that we're using very low heads. It's designed using local materials as far as possible. And because this whole facility is being run on renewable energy, we need to keep the power consumption as low as possible. So we're basically pumping the water as low as possible within the facility. The last part of the mix of technologies in the project is the monitoring and control system. So we have Oxyguard as a partner in the project, who are taking care of the monitoring and control of both the RAS part, but also of the energy part and the wastewater treatment. The objective of this part is to design something which is low cost. In all the projects, that makes no sense if this is completely unaffordable. So the system has to be affordable in the local context, which is not an easy job. So the novelty in the monitoring and control system is the reduction in cost for what we need. So it is based on the normal Oxyguard system, and we're taking the O's, the typical, and from the RAS system, and then from the membrane bioreactor, the TMP, pressures and stuff like that. So yes, if this gives an overview of. If you're interested in learning more about it, we have a stakeholders community, and you can speak to us, and we'll be glad to have you with us.
Thank you.
Thank you.